So calculus, we are in 6.6, doing a thing called L'Hopital's rule, named after a French mathematician that I'll read you a weird story about in a minute out of the book. But what they're trying to tackle here is basically problems that are like 0 over 0 problems. And we had a conversation about this earlier this year when we were doing our limits, chapter 2. But sometimes this is a conversation that even comes up in younger grades, like algebra 1-ish. I think I tease this conversation a little bit. Problems where you have 0 divided by 0 can incite quite an argument among groups of young people, because some people will argue correctly that 0 on the top of anything is always 0. Like 0 over 1, 0 over 2, 0 over 3, 0 over 4, those problems are 0 answers. So some people get a problem like this and they want to argue that this would have a 0 answer, which is true sometimes. Other people will argue 0 on the bottom has no answer. 1 over 0, 2 over 0, 3 over 0, no answers. That's true for those, but in this context that's true sometimes. People will also argue 0 divided by 0 would be 1, because stuff divided by itself is usually 1. 2 divided by 2, 3 divided by 3, 4 divided by 4, certainly are all 1. 0 divided by 0 is 1, sometimes. But sometimes the answers are like 7. Okay, so this has been an argument that's been going on for about 500 years or more back in the history of math. So here's a weird story from page 390 that talks about the history of this thing. So it says a misnamed rule, because it wasn't actually L'Hopital that came up with this idea, even though the rule is named after him. It says in 1694, John Bernoulli agreed to accept a retainer of 300 pounds per year from his former student, L'Hopital, to solve problems for him and keep him up to date on calculus. So, like, I'm Bernoulli in this story, I guess, if you want to imagine it that way, and one of my calculus students would grow up to be L'Hopital, and you'd come work for me and do math for me whenever I was too busy. You'd help me out. You'd be like my assistant. So one of the problems that he hired L'Hopital to do was the so-called 0 over 0 problem, which we are, oh no, I'm sorry, Bernoulli, you'd be hiring me, got it backward. So L'Hopital became like the dominant math guy. He hired Bernoulli to help him out. So you're L'Hopital, I'm Bernoulli. But one of the problems was the 0 over 0 problem, which Bernoulli solved as agreed. He settles this argument once and for all. When L'Hopital published his notes on calculus in book form in 1696, the 0 over 0 rule appeared as a theorem. So one of you guys writes a book, you come up with this idea in your book that you hired me to actually do. L'Hopital acknowledged his debt to Bernoulli, and to avoid claiming authorship over the book's entire contents, had the book published anonymously. Which sounds fair. You wrote a book, but it was my idea in your book. You don't even put your name on your book, and you write me a credit in the book and say, hey, TMR, the math wizard, figured out this rule. It's in my book, but I'm not even naming my name, and I give him full credit. So Bernoulli, me in this story, nevertheless accuses L'Hopital of plagiarism, an accusation inadvertently supported after L'Hopital's death in 1704 by the publisher promoting the book as L'Hopital. So L'Hopital dies, and Bernoulli's accusing him of all this stuff that he didn't even do. By 1721, Bernoulli, a man so jealous he once threw his son Daniel out of the house for accepting a mathematics prize from the French Academy of Sciences, which I suppose he wanted to win it, I don't know. So like, now Joseph wins a math award and I throw him out of the house because I wanted the award. Like, that's how nuts this guy was. Bernoulli claimed to be the author of the entire work, the book that was written with no name on it, to try to avoid controversy. Now Bernoulli tries to steal the whole book. As puzzling and fickle as ever, history accepted Bernoulli's claim until recently, so people believed him until these days. But they still named the rule after L'Hopital. So that's sort of a quirky little math history story that has nothing to do with your homework, but it entertains me, so I read it, and you had to watch it on the video. So here's the scheme. This only is set up to do originally 0 over 0 problems. So if you have some kind of formula on top that you plug into and it gets you 0, you have some kind of formula you plug into that gets you 0, you have this debate that goes back hundreds and hundreds of years. So what Bernoulli figured out, and what L'Hopital's rule tells you to do, is take the top and do the derivative, take the bottom, do the derivative, and see if you can plug in and get a different answer. We're not doing the quotient rule. Okay? We're just going to take the top and do its derivative as its own little mini world, take the bottom, do its derivative, and do its own little mini world, and then see if we can plug a number in. So for a problem like this, to see if the rule applies, see what happens if you plug in 0 first. 3 times 0 is 0, sine of 0 is 0, so the top is 0. The bottom, if you plug in 0, would be 0, so this is why this rule was created. So you go to the top and do the derivative of 3x is 3, minus the derivative of sine is cosine. On the bottom, you do the derivative of x is 1, and then you try to plug in again. If you put 0 in, cosine of 0 is 1, 3 minus 1 is 2, 2 over 1 is a grand total of 2. So this particular version of 0 over 0 is not impossible, 0 or 1, it is 2. And without L'Hopital or Bernoulli or whoever you want to give credit to, nobody could have figured that out. This, same thing would happen on this. I'm not going to test these out every time. They're in this homework set because they are following this rule. But if we tried to plug in, we'd have 0 on the bottom. If we plugged in here, 0 plus 1 is 1, rooting 1 is 1, subtracting 1 would be at 0. A 0 here makes everything 0, so the rule applies for this. I feel more like doing the derivative on the bottom first. That looks easier. Derivative of the bottom is 2x. I feel like doing the derivative of this next. This is like a half x as it's written here, and the derivative of half x is half. Derivative of this vanishes. This I think about 1 plus x to the half. So that would be half 1 plus x, doing the chain rule, to the negative half. And then I would try to plug into that. 0 on the bottom is 0. 0 into here, 1 plus 0 is 0, or is 1. 1 to any power is 1. Times a half is a half. Minus a half. The top is 0, the bottom is 0, so we're kind of in the same spot we started with. And the solution is, just go again. Do the derivative again. The derivative of 2x is 2. Derivative of a half disappears. The derivative of this would be multiplying the power down to the front to get negative a fourth. 1 plus x would have a new power, but we don't even care what the power is, because if we're plugging in 0, 0 plus 1 is 1. 1 to any power, this new power included, would be 1. Times negative a fourth is negative a fourth. Negative a fourth dividing 2, if it makes you feel better, put it over 1 and flip it, we'd end up with negative an eighth on that. And then we head over a column. Am I still on screen? For this, if we do the derivative of cosine, it'll become sine and switch to be positive. The bottom would be 1 plus 2x. And then we put in 0. On top we get 0. On the bottom we get 1. 0 over 1 is 0. If they put the little plus or little minus on these, that does nothing. Okay, so I could go back here and put a little minus on that. This just means it's a little less than 0. This means it's a little more than 0. But whether those are there or not, you're basically just plugging in 0. This one I would get cosine on top of 2x. If I try to plug in, I get 1 on top of 0. Now we have to remember a thing from chapter 2, sorry, way back. If you get a number on top of 0 when you do limit problems, you lean toward infinity as your probable answer, but you have to be able to decide on the sign. And in this case, I did need that little plus there. The little plus means we're a little more than 0, which means that this would be a little bit positive, and this would be positive infinity. Without that little plus sign, we couldn't decide on that, and we'd have had to say no answer on that. Then on your notes, there's a break that says, history has discovered over time, 0 over 0 problems, this is good for. Infinity divided by infinity problems cause the same controversy, and this rule can solve them in the same way. So we can do the derivative here to get 1 minus 4x. Derivative on the bottom is 6x. This would still be infinity on top of infinity. So you'd go again. We'd get a negative 4 from doing the derivative on top of 6. And that fraction could reduce to negative 2/3. We had a different strategy for that in chapter 2, which is still true. In chapter 2, we looked for the highest powers on x's. And since those tied, we could just make a fraction out of those numbers. That's like a trick that grew as an offshoot of this rule, but you learned that in chapter 2. If you try to take 0 times infinity, your notes explains that this also works for that kind of a quirky problem. 0 times infinity is really weird to think about. But what we could do on this is use our trig knowledge to make a fraction, x on top and tan on the bottom. And then we look to do our derivative game. The top is 1. The bottom derivative of tan is secant squared. And then plug in. Secant is like cosine, so that's 1. But it's flipped, so it's still 1. Squared, it's still 1. It's in a fraction with 1s, that would just be a 1. It also works for infinity minus infinity problems, the notes describes to you. This would be an infinity minus infinity kind of a problem. But what we can do instead is make a common denominator to get it to be a single fraction. This rule only works if you have one single fraction to work on at a time. So common denominator, we would need both of those. And then if we're making the bottom get new pieces, you have to make the top get a new piece. So this fraction needs to acquire an x. This fraction got a new item with sign on the bottom, so we need that on the top. And then we could look to do the derivatives. 1 on top minus a cosine. To do the derivative of the bottom, you'll need to do a product rule. The first thing times the derivative of the second, plus the second thing times the derivative of the first, and then try to plug in. If we plug in 0, the bottom would be 0, and the top cosine is 1, so that would be 0. So we have a 0 over 0 problem, so go again. Derivative again of cosine would become sine, but reverse back to positive. This would be another product rule. X times cosine's derivative plus cosine times x's derivative plus sine's derivative. And then plug in. We've still been plugging in zeros. Top is 0. Bottom has a 0 here, but a couple of 1s. 0 over stuff would be 0 for an answer. And then the last category is if there's powers involved, there's all sorts of weird power problems, like imagining 1 to the infinity, or 0 to the infinity, or just weird power situations. Suggestion on these is do an ln first, and anything in math that you just like create to change your problem, you'll have to pay for that later. So we're going to do an ln first, and we're going to do an e later as the opposite to pay for that. So if we do an ln, we've learned with ln's that the powers could slide to the front, and instead of writing 1 over x next to an ln, I'm going to put this ln instead on the top. When we go to do the derivative of that, we'll get a 1 on the bottom. On the top, when we do the derivative of ln, it's going to be a fraction inside of a fraction. The derivative of ln is a fraction where 1 plus x, the original, goes to the bottom, and its derivative, which is a 1, goes on top. If you get a bunch of math stuff in the shape of a Christmas tree, and I think my director would verify for me, this is in the shape of a Christmas tree, basically.
Sure.
You've done something about right, because like there's your Christmas tree. But plug it in 0. 0 in here, 1 plus 0 is 1. And if you do 1 divided by 1 divided by 1 again, that's just going to be 1. And it feels like we should be done, but we have a payment to make. Since we did an ln at the beginning, e goes to that power at the end. The best answer is just e. And then I'm over one more column. Am I still on screen?
Problem is you are.
So again, there's a power involved. So I'm going to do an ln to get the problem going. That lets the power go to the front. Instead of writing 1 over x next to the ln could just as easily go on top. And then we look to do derivatives. The derivative on the bottom is a 1. The derivative on the top is going to be a fraction. All ln derivatives are fractions. Derivative of ln x puts the original x on the bottom, and its derivative 1 on the top, and it looks to me like a Christmas tree again. If we put in an infinity here, 1 divided by infinity would be 0. That's like the cookie to China story from early in the year. If you have one thing, one item, and you divide it by infinity, it's like taking one cookie and go to China and share with everybody. It's not going to work out well to anybody get any cookie. 1 divided by infinity is basically 0. 0 dividing 1 is 0. And it feels like you're done, and you almost are. But since you did an ln at the beginning, we need to do an e to that power at the end. And anything to the 0 power is 1, including e. So that's 6-6. We're working on this first day's homework. I think on the syllabus is the odds. If that's difficulty, we can spend a day doing the evens. And if you're not liking that, email me and we'll figure out a way to do a little bit of interactive help. I would think this lesson flowed a little bit better than the 6-5. The 6-5 I think is a much harder homework set because there's a lot of variety of what you do. There's not much variety of what you do today. Make sure you have one single fraction, so maybe a trig trick or a common denominator to make sure you only have one fraction. But if you do have one fraction, derivative on the top, derivative on the bottom, plug in the number that they gave you. Hope that you're done. If it comes up still 0 over 0, just keep doing the derivative as many times as it takes until you don't have 0 over 0 anymore, and that should play out. The problems are much more similar from problem to problem. Big emphasis, I've had some people sometimes look at these fractions and they're so used to derivatives and fractions being quotient rule, they get caught in that mindset. And it's not that at all. The top do its derivative as its own little world. The bottom do its derivative in its own little world. You start with a fraction, you become a smaller fraction as you do the derivatives. Things should clean up and get better as you go. That's it.